Good morning. Welcome to Prime Time at the Bethel University Library. I'll have this here just in case. Prime Time is a collaborative program between the Friends of Bethel University Library, Academic Affairs, and other offices on campus that brings you programming that celebrates learning in and beyond the classroom of Bethel faculty, students, and staff. We're so glad you've joined us. Before we introduce today's presenters, we want to invite you to join us next week for two great presentations you won't want to miss. On next Tuesday, March the 8th, Dr. Janine Brown, Director of Online Programs for Bethel Seminary and a New Testament scholar, will share about her experience writing a commentary on the book of Philippians, which has just been published as part of the Tyndale New Testament Commentary series. And a week from today, on Thursday, March the 10th, Dr. Susan Brooks, Professor of English, will share about her recent research in a presentation titled Shifts Happen, Negotiating White Evangelical Backgrounds While Building Identities as Anti-Racist Teachers. Today, I'm delighted to welcome you to an Edgren Scholars presentation. The Edgren Scholars program supports faculty-student research teams as they collaborate on a summer-long research project. The project must be one that has the potential to make a significant contribution to a given field of study, and the project must reflect meaningful collaboration on research between students and faculty. The Edgren Scholars program is named after John Alexis Edgren, the founder of what is now Bethel University. One of the key educational principles that Edgren articulated in the 19th century was this: the relation between teachers and pupils shall not be that of commander and subject, but one of true friendship and helpfulness. It is in this spirit that we established the Edgren Scholars program in order to encourage and facilitate students and faculty working together. Dr. Charlie Goldberg is Associate Professor of History and Digital Humanities, and Zach Haala, a senior majoring in Software Project Management and Digital Humanities, are one such Edgren team. Charlie and Zach spent last summer building artificial intelligence models to do digital humanities analyses. Let's learn more about their fascinating project.
Thank you. Thanks, Ray. Do I sound okay? Levels are good? Great. So I teach in the history department, and I also teach in the digital humanities program. And I do know most of you here, but if you're not familiar with digital humanities, I think this is a really good introduction to the kinds of work that we do, and in particular today, how it can contribute to research and scholarship in history in particular. So it may seem like a strange combination to look at artificial intelligence through the lens of history. But when I sat down to think about the possibilities for this kind of project, the more this combination actually makes really logical sense to me. So as a historian, I am particularly interested in pattern recognition. For me, my data is literary history. So people like Livy and Tacitus are ancient historians. And when I do my research and scholarship, I sit down and I look at my data and I look for patterns in the past. When I see a pattern emerging, that's historically relevant to me. It gets really exciting when I see those patterns start to change. I mean, that's what history really is. It's changed through time, changing patterns. A lot of times, as historians, it's a pretty solitary endeavor, right? Modern historians might go to archives alone, read and research alone, write alone. And so in some ways, we're really limited by what a human brain can analyze, how much data we can process. And that's actually where using artificial intelligence holds a lot of promise. Artificial intelligence can analyze humongous amounts of data, whether that is a Spotify playlist suggesting to you what songs to listen to after. It could be self-driving cars recognizing, the border of a lane of traffic or the car in front of you. And as we can see, I mean, there's some ethically challenging uses for artificial intelligence to recognize patterns and things like police enforcement. We'll get into some of those details later. But this is what I see as resonating between what I do as a historian and the kinds of things that I do in digital humanities. And so I do see this clear connection there. I will admit, though, that when I started looking at artificial intelligence, I didn't have any clear roadmap in mind. And when I started looking at it was in the advanced digital humanities class that I taught with Zach a couple years ago. And I mainly added a week on artificial intelligence as kind of a breather in between bigger projects. And honestly, I was just looking for ways to have fun for a week without a clear goal in mind. And actually, this is really easy to do, to find fun things to do in AI. So on the left here, this is just a screenshot from one of many Google experiments. So I recommend just Google experiments in AI, and there are all sorts of easily accessible tools and games to teach what AI is and how it works. So we did things like that. We also did some rather uncanny experiments as well. So this is a person that is fake. He doesn't exist. I refresh, either does that person. Right, these are all computer-generated people that look strangely real. This cat is also fake, I'm sorry to say, as is that one. So again, I did not have any real, tangible, scholarly goals with this, other than to explore what AI can do. But it didn't take long for a more historical task to emerge. And so when I sat down and I started to see what AI could do, it seemed to me that it had a lot of promise for how historians do their work. So I began to look for a good data set that I could use as a test case. And obviously, as you can see here, the data set we chose doesn't have anything to do with ancient history. So in particular, I wasn't really interested in asking AI to do a task that helped with my own research as an ancient historian. I was more interested in just asking, what can artificial intelligence do for historians, for humanities researchers? And working with Kent Gerber and the Digital Library, we have used this data set to teach in digital humanities before, so I was somewhat familiar with it. So this is the Bethel yearbook collection. And this is the data set that Zach and I used for our summer project. It was published in most years from 1909 to 1989. There are some gaps because of wars, and then it kind of does peter out in the 70s and 80s. So the benefit of using this data set is that because of Kent's great work, it was already really easy for us to use. So this is contained in the History Center at Lakeside in hard copy, but Kent has scanned them. OCR, which is optical character recognition, which is just converting the text you see into computer legible text. So we had 73 of these in PDF format ready to go for us. Like I said, I'm not a modern historian, I'm an ancient historian, so I did feel a little bit diffident about studying 20th century history with AI. But I also recognize that yearbooks are a really great way to study the past, and photographs in general are. In particular, other scholars who have used computer techniques have recognized that they're just a really great visual format through which one can examine changes in content, from personal style to developing social norms. And I also think it's really easy for all of us to see that we know something about the history of photography, just as visual learners. So you can see real differences here at the beginning of our data set and how people sat for photographs. You know, the old-fashioned way of just sitting stoically, no smiling. And then over time, people sit more casually, they smile. And I think that we as human beings can recognize these changes through time. So in other words, what I'm saying here is that when we asked the computer to recognize patterns, we were asking it to do so in a way that we as human beings could easily verify, because we know that there's a transition from the beginning to the end of our data set. So we wanted to test the computer to see if it can perform some of the tasks that human beings could, but at larger scales. So I'll turn it over to Zach in just a minute, but that's what I wanted to get out of this. And so I want to hear from Zach, too, about what he was hoping to get from this project.
Yeah, going into this, I was out the gate super ecstatic that we were going to be able to run this project over the summer. The biggest thing for me was that I was able to combine my computer science background with my passion for history. And thanks to Dr. Goldberg, even if it was on a minor scale, I was able to be a historian of sorts, at least for a little amount of time. Being able to take in the data and things we found in our research and analyze those trends over time was something that was super cool to me, as opposed to simply doing the coding or whatever else needed for Dr. Goldberg's side of the research. So that whole process was super rewarding for me, and yeah, that's what I looked to get out of it. So.
Yeah, when we were interviewed by the comm marketing team, one of the lines that Zach said really resonated to me, that he's not a code monkey. If you've heard that term before.
Right.
So like our workflow was really collaborative. I think I've gained enough programming skills over the years to be somewhat competent in it, but not nearly as competent as Zach. But the reverse is true as well. I mean, I'm not an expert on 20th century history. So we found insights together, and Zach will comment on some of the historical findings that he saw throughout the project. We did have some larger project goals or research questions that we started with. And the big one was simply, can the AI recognize changes in photographs? And we kept that really broad. Our first experiment, as you'll see, starts with smiling, because that's a clear difference between the beginning and the end of our data set. But we also wanted to know that what other sorts of differences could the AI recognize: fashion, eyeglasses, earrings, necklaces, things like that. We also asked it to look at the people in more detail. So things like gender and age range and ethnicity. And as you can tell with some of those questions, that we're kind of getting into some ethically challenging territory with that. And we'll talk a little bit more about the findings and some of our conclusions on the ethics of using some of these. Most of what we did has to do with a process called object detection, which is a computer recognizing that the thing in the picture is a particular thing. So here it's a dog, but it could be a smile, could be earrings, necklaces, etc. So all of this has to do with how computers look at an image, which is really differently than how human beings do. So Zach's going to give a deep dive into how a computer views an image.
So yeah, bear with me here as I kind of go into some of the more technical things with object detection, like Dr. Goldberg talked about. So I'm going to start off with talking more about the specifics of image recognition. That is the concept of passing an image into what is called a neural network, in which that neural network takes the image, processes it, and returns a label for that image. Before I explain in greater depth about what a neural network is, I'm just going to explain how a computer simply views an image. Let's take this image of a dog, for example. As you can see here, we're zooming in on the area surrounding the dog's paw. As we look closer, we can see that all it really is a series of individual pixels within a defined area. Each pixel, in turn, is made up of a mixture of three colors: red, green, and blue. An image file on your computer actually just stores these three separate images, one for each color intensity. The image you see on the screen is really just a combination of those images. Your computer reads each pixel for those intensities with a number from 0 to 255 corresponding to how intense the color is at that point. 255 being closer to brighter pixels and darker pixels having a value closer to 0. As you can see, your computer simply takes the numbers corresponding to each pixel and stores them as a two-dimensional array or a list of sorts, with each pixel simply being represented as 3 numbers, that intensity for red, green, and blue. Sometimes that process can be simplified even further by converting the image to a grayscale, in which the computer then just stores a single number representing the color intensity for that gray level. Many times for this process to run even smoother, images need to be downscaled to a size of about 256 by 256 pixels, so that the amount of necessary computing power required is greatly reduced. If images are too high quality, or there's a great number of images being run through a program, those processes can take a great deal of time. For some of the experiments that we ran, due to our large data set of photos, programs ran for upwards of 8 to 15 hours at a time. And that was with downscaling the photos and optimization of some fairly powerful computers. As we move forward here, I'm just going to talk about the process in which a computer recognizes specific objects with images, as opposed to simple image recognition itself. So to recognize objects within images, models must be created and trained to recognize patterns in those images. To do so, models are given a set of training images containing the same object, and subsequently can then determine whether these photos do or do not contain that object. Let's look at a basic example of a model that is trained to recognize handwritten 8s. A model like this is fed a bunch of pictures that contain the handwritten number 8s. As seen here, we then tell that model that these images do contain that object. Afterwards, that model is then fed images that to humans, it is pretty obvious that they are not handwritten 8s. So then we go on to tell the model that these do not contain that. This is called training the model, and the model then looks for patterns in those images, and when fed more images later on, can then in turn recognize when those images do or do not contain that object based on the patterns it does or does not identify. Remember when I kind of touched on the topic of neural networks a little earlier? Well, models that are specifically trained in image recognition are often called neural networks because they operate similarly to how our brains do. That is by passing data and information from one node to another, going through layers and looking for patterns and such until an object within an image is recognized. On the base level, as we see here, when a neural network is given an image with the number 8, we must train it to produce the results we're looking for. In this case, as it is fed images that contain the number 8, we tell the neural network that it should eventually spit out a 1, corresponding to a true value that the image does contain that number 8. On the flip side, we also train it as such that it is when it is given images that do not contain that number 8, it returns a 0 corresponding to a false value for finding that number 8 within the image. When the training process is complete, new images can be passed to the neural network, which then generates a prediction or a probability of sorts, whether that image contains the object we are searching for. As you can see here, with this example of this 8, when passed to the neural network, the model has returned a confidence value of 0.98 that an 8 is in that image. At a certain point, usually closer to 1, you can trust that the model, that what it has recognized does actually contain the object you're looking for. That kind of tipping point or baseline number that you decide to go with, whether it's around 0.9, 0.95, really depends on the types of images you're using, how powerfully trained your model is, and how exact you want to be on your research. And so over here, we can see that this number 7, when passed to a neural network, has given a probability of 0.04 that it is an 8, which obviously to all of us, we can tell with almost certainty that that is not an 8. But when passed to the model, one or more patterns had been identified that looks similar to what an 8 would contain. Likely, this is the area here where it starts up in the upper right-hand corner and works its way down to the left and diagonally, as in like an 8 does. So these types of patterns are searched for each by passing through what are called convolutional layers. These convolutional layers are looking for a specific pattern within the image, and let's just dive into how that works with our 8s example. So, as we can see here, each node in the model represents a pixel within the picture. As each node goes through the neural network, it goes through a great number of these convolutional layers that I was talking about. The more layers that you have, the more accurate that your model is going to be at correctly identifying the objects you're looking for. The trade-off there, of course, is that with more layers, it takes more time and potentially more computing power to run those processes. Each convolutional layer looks for a specific pattern. For example, one layer may look for a pixel starting at the top left corner of this 8 here, and then check to see if following pixels of similar color intensity continue to work upwards and toward the right. When this happens, the model makes a note of that. Another layer would look for a completely separate pattern. And when the model has seen that enough of these patterns emerge, the model can then make a decision at a confidence level that the object was or was not in the image. It does so by eventually spitting out an output layer that contains a number of output nodes. These output nodes each correspond to an object tagged with a label describing the object it is looking for and giving it that confidence number I was talking about, or a probability of sorts. This is on a scale of 0 to 1 of whether the object that the model is trained to recognize is contained in the image or not. Looking at this example here, it is given that this 8 returned a probability of 0.96 that it contained that object. One of the main processes that we performed in our research was specifically facial recognition. So it's just that idea of object recognition, but specifically looking for faces as opposed to 8s like I was just talking about. So here's how one of those processes works. With simple image detection, we can only identify color changes in individual pixels. With a process called histogram of gradients, or HOG for short, we can extract the gradient and orientation of the pixels to then produce an edge and direction. In this process, the image is converted to grayscale, and a cluster of pixels is examined to measure changes in pixel darkness, as well as the direction of change. This is done with each grouping of pixels over the entirety of the image. This ensures that the object that we are looking for is not missed, and then as the process goes through, each pixel is eventually converted to a gradient line. So this is the zoomed in version of this person's eye here, and then as it is converted to those gradient lines, it'll look something like this. The good part about this is that to humans, this is still somewhat recognizable. And as we move on here and look at it on the broader scale, we can tell that this is most definitely still representational of that person's face. So as you can see from the broader view here, this is the way in which facial recognition can become a much more detailed process. And from this, we were then easily able to perform some of the experiments that we did on the yearbook photos. So HOG is just one of many techniques used for object recognition. One precursor to more modern facial recognition techniques is called the Har Cascade process, which we ended up using in a few instances where we deemed that it was plenty useful enough for what we were trying to accomplish. It works similarly to HOG in that a window passes across the entirety of the image, cascading essentially, that looks for patterns within the image. The difference is that it simply takes the pixel intensities in each region that it is passing over, sums them up, and calculates the differences between the sums to identify patterns. All right, before we move forward here, I'm just going to give a brief overview of our workflow for the project that we did over the summer. We began with those scanned collection of Bethel's yearbooks in PDF format that Dr. Goldberg had talked about how Kent did that for us. And then we took those PDFs and converted them each to image formats so that they were easier to work with for what we wanted to do. We then used a Har Cascade process, like I just had mentioned, to then scan and extract each and every image from each and every yearbook page. All in all, this left us with around 20,000 images of faces. And although having a high rate of success, this process was not perfect. So there were still some instances where our models found things that were not faces and marked them that they were, and then the flip side where it missed out on some faces and identified them as not being so. To clean this up, we decided to use another Har Cascade process to then sort the images by gender and year. And it was with this baseline collection of faces that were cleaned and sorted that we were then able to run many of the experiments such as smile detection, gender sorting, ethnicity recognition, age identification, that sort of thing, and much more using processes like HOG and a number of others that Dr. Goldberg will kind of go over now. So, thanks.
Okay, so we're going to get into some of our findings here in just a second. But I really briefly first wanted to give a little more detail on how specifically facial recognition works. Picking back up from what Zach covered with HOG and Har Cascades. So facial recognition actually converts an image in the same way that Zach mentioned, and it overlays what you see here on the right, which is called facial landmarks. So this is a series of convolutional layers on the top right there, where each point on the human face is assigned a different layer. So as it looks at a picture of a face, it is trying to recognize where those points line up on that particular face. Our first experiment was for smile detection. And so on the left, it's a little bit small if you're sitting far away, but you have a girl's face here from not smiling, progressing to large smiles and everything in between. And below, you would have how that arrangement of facial landmarks would look when the computer is trying to recognize a smile. Top right is real Bethel yearbook photos, which correctly identified a smile versus no smile. As Zach mentioned, though, our process wasn't perfect. There were several instances where a face that clearly is smiling was not recognized as containing a smile. Many of the faces that were missed the most were non-white faces. So we'll come back to issues about using this process in regards to race and ethnicity and gender. But we clearly, as the humans who are watching the computer work, we recognize that this happened. Not an overwhelmingly number of times, but enough to be noteworthy. And we also recognized a fair amount of false negatives, right? So like, this isn't a face, but you can also kind of see how a computer might think it's a face. So anyways, it wasn't a perfect process, but we were satisfied with most of our experiments that it was accurate enough. So this is our first graph that we produced, and I'm sorry it's not so easy to read in person, but starting in 1909 here, moving to 1989, and non-smiling faces are in blue, and so in the early years, close to 100%, depending on the year, didn't contain smiles. And then at some point in the late 30s, early 40s, really the early 40s, the number of smiles skyrockets as the non-smiles come down. And then there's some decades where it's a little messy. It kind of depends on the particular yearbook. But then it does seemingly resolve towards the end of our data set in the 80s, where the majority of faces contain a smile. So like I mentioned, I'm not a 20th century historian, but I know enough about the 20th century to make some conclusions here. And Zach actually did a great job of spotting things that I didn't notice. So do you want to mention the football example?
Yeah, so obviously we see this trend of smiles becoming more prevalent as the decades go on. But we see here around the early 60s, it takes a dip before it goes back up. So something that I realized when looking through the images in the whole yearbook pages was that this is around the time when sports at Bethel kind of picked up, especially like things like football. And so we see those trends dip because there's so many faces within this one image. And these guys are all mean mugging it because they're football players, right? In the 60s. So that is one reason why you can see that those smiles kind of take a dip before they go back up. So
the other really interesting thing we noticed on this graph is that in the early to mid 40s, there is a huge increase in smiles in photographs. When we get to another experiment in just a second on gender, you can also see that the number of women in the photos also increases. So I think we're seeing here some kind of a gender norm of when people are starting to smile more, it tends to be more women than men. This is also the years when many of our male students were probably fighting abroad, which leads to an increase in women in the faces as well. This is also another kind of a fun variant of the smile experiment. We did what's called face averaging, where the computer finds the average facial landmark arrangement by gender and by decade, and then it forces each individual photo to that average. So you end up with individual photos that look strange, but the average emerges as that is the average male Bethel student from that decade. And then the pixel value, the average one, is just put on top of that. So you end up with a clearly recognizably human face. And it's also an easy way to see the progression of smiling from the teens into the 80s. So we made an animated GIF of that model working. Our next experiment was about gender, and you can see some similar findings from the smile experiment, especially in the early World War II years, with more female students showing up. The other interesting spot on this graph for us was in the early 70s, late 60s, and so Title IX is in 1972, I think. And so in the years preceding that, you see another increase where the number of female students actually finally gets back to the level that it had achieved during World War II. So this would kind of confirm something that a lot of scholars have recognized, that in the post-war years, gender norms return to the pre-war arrangement, and it does take a couple decades before progress catches back up. This one's a little messier, but it broke down students by age, and especially in the early years, it's hard to discern any pattern other than there are students from many different age groups. As time goes on, and especially as Bethel becomes more of a four-year undergraduate institution, you start to see more photos of people in their late teens and 20s, which is the blue line. Now we kind of get into some trickier territory, which is in regards to race. So we ran a couple experiments that tried to identify race and ethnicity by photo. And as you can see here, it didn't do a great job. The top line is predictable, and that's white. But the second greatest race or ethnicity was actually an error. So this is the error line where no clear result emerged from the data. So I guess I don't personally know enough about our institutional history, but I think as a school we remain overwhelmingly white in the 20th century. I think our evolution towards more racial diversity doesn't really pick up until late 20th century, early 21st. So in some ways, I guess this confirms that But I also want to talk briefly, though, a little bit about how AI is problematic in regards to race and ethnicity. For our purposes, non-white faces actually are not picked up by AI techniques, the ones that we were using. And that really is more of a problem with photography. White faces show more contrast. And this is a process that relies, as Zach mentioned, entirely on contrast, both in the face and on the edges of the face too. So this has been seen in a lot of other contexts, but it's just a fact of the technology that non-white faces are not recognized at the same level that white ones are. And we saw this in our own data. As you can see here, one of only 2 faces that wasn't picked up as a human face is an African-American male face. And then we mentioned that not all the smiles were picked up too, and we noticed that there were more non-white faces that were not picked up than white faces. We did want to compare some of the race and ethnicity findings in the images to some textual data. So Kent and I prepared this for another class. It was more limited, so we really only picked 4 years every 15, 20 years or so. But we used the rosters. So in some yearbooks, it would say the student's name and hometown. So we converted this to text. And then we ran a couple experiments. One that compared the student name to some other AI program that attempted to identify ethnicity based on names found in Wikipedia. So if you go to somebody's Wikipedia page, it might say where they're from. And so this was then comparing Bethel students to that database. And this one was probably the most wildly incorrect one that we did. So apparently we're an overwhelmingly British school. And coming in second is European Jewish ancestry, which for an evangelical school is probably not the case. It did pick up, some significant Nordic element, which is probably true, but I'm guessing that that's much higher in reality. The second text experiment we did compared names to census records. And so when you fill out the census, you can supply what ethnicity you're from. So maybe this one is a little more accurate, but it's also more limited. It only asked about 4 ethnicities, and again, as an overwhelmingly white school in the 20th century, that's the result that we found as well. Let's see. Okay. I won't get into the details here just because this is so difficult to read. But I will note that all of these rely on probabilities. So when I say 80% British, what that really means is that that's the largest probability for any particular last name. So it might say there's a 68% likelihood that that's a British name. And so because that's the highest recognized ethnicity, it's counted as British for our tests. We also had a limited experiment on fashion that we weren't able to bring to fruition as much as we did the other ones. This was a simpler task that involved using cloud-based software to drag a bounding box around particular fashion items. So this is like, some of this stuff can sound intimidating if you don't know programming, but it's becoming easier to do. So you simply sit down and you yourself as a human being label objects in photographs, which trains a model for you to then take to your own data set. So it's becoming much easier. This still did take some coding at some point, but the technology is moving so quickly here that I do think that this is going to be pretty accessible to most humanities researchers at some point. Our last experiment, so because we kind of got into some morally dubious territory, we just decided to go full throttle. So a computer's facial recognition, a computer can tell an attractive face from an unattractive face. So we just thought, well, we might as well just do it and see who the most attractive Bethel student of all time was. And according to science, it's 1989 grad, Joel Fredrickson. So congratulations to him. So our overall findings, This is absolutely something that's worthwhile for historians to use, for anybody that's interested in visual culture. Because you can train the AI to recognize any pattern that you're interested in. The text analysis, my understanding is that it is probably as promising, but we just didn't focus on text as much as we focused on photos. There was a very powerful model released in 2020. So for us as professors, students are going to have a very easy time generating a very convincing CWC paper if they are so motivated. So we have to look out for that. And again, probably our most interesting finding as scholars has to do with some of the pitfalls of using this technology for race and gender and ethnicity in particular. Thank you. So maybe we'll open it up to questions, comments. Yeah, Omar.
I have a technical question for, I guess, for Zach. So I'm trying to understand the probabilities, and I'm not sure I fully understand it. So imagine two different models that are, one is much more powerful than the other one, because we fed it way more images to teach it how to recognize 8 better. Are they both going to spit out the same probability if they pick out the same amount of nodes?
Potentially. The more powerful model that is trained with more images is more likely to be more accurate. Depending on the patterns that you are looking for, a weaker model may get lucky and recognize those patterns within an image, but a more powerful model will recognize those patterns, with a higher probability of that happening. If that makes sense.
Yeah, I mean, it's true that it'll recognize it with a higher probability, but it seems to me that they'll spit out the same probability, because if you fed it like 10 images, and this one you have 100 images, and then this one picked out one node and this one picked out 10, it's going to spit out the same probability, it seems to me. But it's very clear that the more powerful one is more accurate, even though to us it's the same probability. Right? That seems to be. In other words, the probability doesn't seem to be conditioned on the power of the system, which is something that seems to be necessary to see whether the probability is accurate to how powerful the system is.
Right. Yeah, that's true for the most part. I think I get what you're saying. The only thing is that when it is fed more images, there is also the possibility of it picking up patterns that are not within it, which could then reduce the confidence level. Does that make sense?
Yeah.
So on the flip side, you can find things where although it matches up the correct patterns, both of them do, being fed 10 versus one node, the extra nodes could find things that aren't within the image and give a lower confidence level potentially as well. It goes both ways. So that's why it could eventually, spit out the same number. But you can just say with more confidence that it is going to be more accurate per se, even though the numbers might match up. That makes sense.
Okay.
Did you have, did the AI get better as time went on? Did you allow it to continue learning? Or once you trained it to a certain point, did you just said, okay, now go have fun?
Mostly, well, I guess a couple answers to that. A lot of our experiments relied on pre-trained data. So smile recognition, sorting by gender. We used models that other scholars have created on that. Where we trained our own model was here. And we had some issues with it. I think we were confident enough that even if it wasn't recognizing the object as high at as high a rate as the smile recognition, it at least was inaccurate across the board by decade, by gender. So some of this, my medical expert wife reminded me that if I'm calling these experiments, am I using the scientific process? And the answer really is no. So maybe that's a weakness of our experiments, but maybe tests is a better word. But long story short, we really subjected this to the eyeball test. Are we happy when we look at the photos? does it seem like they're recognizing the things that we're asking it to? Sarah?
I maybe prematurely raised my hand because I'm trying to make sure, I don't know if my question will make sense.
Sure, yeah. Just
But the limitation of the models to identify faces by race and ethnicity, is that to some degree because the models were pre-trained in a norm that's predominantly white? So like if you wrote a program in a culture or in a context where your photographs are predominantly darker skinned people, is it possible to create a technology that's actually better at that?
yeah.
Yes, to a certain extent. If you're going to train your models with a predominantly, darker skinned, images being passed in, they may be more accurate, but it is really the limitations of the technology right now to identify the contrast in those pixels that are within the image, and that that's more of a technology limitation with photos than it is a training your model effectively kind of issue.
Yeah, that's what I would say too. There was an article a couple weeks ago that resonated with me that wasn't about artificial intelligence at all, but it was about photography. And actually, new cameras have been engineered specifically for non-white faces. So maybe in the future, we can kind of get over this inequality. But historically, if you use historical data sets that contain images, you're likely to have that issue, would be my guess. Yeah. Ken, yeah.
Are there any other things that you noticed maybe that you weren't able to pack into the presentation? So like, I was fascinated to hear about the football team's impact on the smile. Or is there anything else that you noticed, just a pattern that popped up that maybe wasn't as large or but was still interesting? Or?
I don't know. Does anything come to mind for you? I would say there was still a fair amount of noise in the results depending on the year. And a lot of that has to do with who designed that particular yearbook. So you have some that are full of more portrait-y faces, like on the right here. But then you have some, especially like in the 70s and 80s, that are very casual action shots. And that I had to take out some years because you see wild spikes that have less to do with real trends and have more to do with I guess, incomplete data from that year.
Yeah. One thing that I would say that I recognize is we get to a certain point where there is a decade or so where men tend to have much longer hair, and that can come to.
Oh, we wanted to do a hair one.
Yeah,
we didn't get to it.
where then the models sometimes had issues determining gender there because they had similar hairlines to women. So
Sure.
that was something that was kind of interesting to see as well, where there was some discrepancies there. But
I would say too. I mean, gender is just as dicey as ethnicity. I mean, maybe gender norms in the 20th century on the whole might be more stable than today. But if you do plan on using this technology today, you're probably going to come across the same issue of a computer recognizing a face incorrectly based on gender too. I forgot about the hair thing though.
yeah.
Well, I think we're probably just out of time. So thanks to everybody for coming. Come and talk to us if you have other questions too. Thank you.